Today, we're going to talk about chapter one from Wade, which is basically an introduction to organic chemistry. There's going to be a lot of review in this chapter that you should remember from your general chemistry classes. If it's not review, if it seems new to you, that's fine too. So don't panic if this is new. Generally speaking, organic chemistry is a very cumulative course, meaning that it builds on previous material as it goes. And chapter one of organic chemistry is already going to build on general chemistry. So actually, we're going to do chapter one in 2 days. We're going to do kind of the introduction to structure in lecture one. And then on Wednesday, our next lecture, we'll move a little bit into bonding and reactivity. So let's start with a little introduction about what is organic chemistry. So probably what you've heard of before with organic chemistry is that it's based on carbon, right? Organic chemistry is the study of carbon-based molecules. Why does carbon get its own topic? Well, carbon's really important, mostly because carbon-based molecules are the foundation of life. All biological molecules are carbon-based. And it turns out that the type of chemistry that is based on carbon is widely variable, lots of diversity. And so it's just a very interesting field to study. Organic molecules, they are composed primarily of only a few elements: carbon, hydrogen, oxygen, nitrogen, sulfur, and occasionally a few other elements like the halogens or other miscellaneous ones. So really what we're doing is we're going to only be studying a tiny little section of the periodic table. Whereas in general chemistry, we spent some time talking about all aspects of the periodic table. In organic chemistry, we're going to focus on only a little tiny corner up in the top right. Okay. So, all right. So carbon is really special. Like we said, it forms unusually strong and stable bonds with atoms that are near it on the periodic table. So if you think about it, what type of bonds would these be? Carbon is on the top right of the periodic table, and it's making bonds with atoms near it. So we're making bonds between nonmetals and other nonmetals, right? Those would be covalent bonds, okay? It can make bonds to 1, 2, 3, or 4 other atoms at once, and those bonds can have various geometries. And when you combine various geometries, it gives rise to various molecular shapes. So again, diversity in structure. It is, of course, plentiful in nature. Its compounds are easily manipulated in the lab. They tend to be stable, which is nice because they have long shelf life. They can be used for things, but they're also reactive enough that we can modify them to our heart's content. So like I said, we're only going to be focusing in on a little kind of corner of the periodic table for the entirety of this class. Anything about metals, the D blocks, the F block, all that stuff, we're just kind of going to ignore for a while. Now, I made a crucial mistake when I took organic chemistry as a student. The first several lectures that we had in our class were about all these little details, and none of the details struck me as particularly important, meaning that, the teacher would talk about them and we take notes on them. And when I'd go back to study them, it was always like, well, this is what's so important about this? Like, what's the deal? What's the big picture? And I kept waiting for the big picture and never really got there, never really came to the big picture. And then we took the exam, and the entire exam was all these details that I had just swept under the rug as being insignificant. So my reminder to you is that this class is about the details. You are responsible for the details. The fact that we are focusing on such a narrow little sliver of chemistry means that we have lots of time to really dig in to the details and learn the nitty gritty about this stuff. So when it seems like we're being picky or really getting into the nitty gritty or wasting time on all these what you might think are minor, that's what the class is. Okay. So that's my warning to you from this point forward. Don't brush aside the details. That is the important part of this class. Okay. So organic chemistry, in a lot of ways, is really a model science. It's a beautiful science. Remarkably complex structures, things like DNA, RNA, and proteins, can be formed just from simple building blocks that involve carbon, hydrogen, oxygen, nitrogen, and only a handful of other elements. So again, just a few building blocks can give rise to enormous complexity in these structures. And even relatively simple structures can have enormous impact. So I've got some structures here. These are things you're probably familiar with: cocaine, morphine, nicotine, testosterone. These are relatively small molecules compared to DNA and proteins that might have thousands, hundred thousands of atoms. These structures here maybe have 20, 30, 35, 40 atoms altogether. But as you know, these are quite impactful things. They can have enormous impact on biological structures. By the way, the notation that we're using here, we're going to talk about this a little more later, but these lines and angles that you see here represent carbon. So here's a carbon, there's a carbon, there's a carbon, there's a carbon. So all of these kind of lines and angles represent carbons and bonds to carbon. So these structures, as you can see, are mostly carbon kind of scaffolds, right? They're carbon scaffolds that have other atoms attached to them, kind of decorated with a few other non-carbon atoms. Another aspect of organic chemistry is that very small variations in structure can lead to large variations in behavior. One of the fundamental principles that you learned from me if you took general chemistry with me was that structure relates to function. Okay. That's the deep, dirty secret, that if you can understand the structure of something, if you know everything about a certain structure, you then can kind of infer from that what its function is going to be. So that is also true in organic chemistry, that small variations in structure can lead to large variations in behavior. I've got a couple examples here. Here are two molecules that look very, very similar. This is called S-carvone, and this is called R-carvone. And if you look at these structures, they look pretty much identical. There's a 6-carbon ring with a double bonded oxygen, a single carbon branch here, a double bond, this little 3-carbon branch with a double bond. The only difference that you will see between S-carvone and R-carvone is this bond right here, that bond there, and that bond there. You'll see that in S-carvone, that bond is depicted as a dashed line, and in R-carvone, that line is depicted as a wedged line. That represents a 3D direction. Essentially, the dashed line, S-carvone, that bond is going backwards, kind of into the board, into the screen. And in the wedged line means that the bond is coming out at us. Okay. So the only difference between S-carvone and R-carvone is the direction that that bond is pointing. But as you can see, S-carvone smells like caraway seeds, and R-carvone smells like spearmint. Completely different behavior, okay? Only resulting from the direction that a bond is pointing. A similar thing is true for fumaric acid versus maleic acid. These have the same structure. Notice that these are two molecules that have essentially the same connectivity. The only difference that you'll see is the geometry around this double bond, okay? Fumaric acid is a trans double bond, and maleic acid, that is a cis double bond. Very different molecules. Fumaric acid is an essential metabolite. It's basically a vitamin, and maleic acid is a toxic irritant. So again, small variations in structure can lead to large variation in behavior. Again, it's the details that matter. If you just ignore that bond, you'd say that these molecules are the same, but they're not. You have to look beyond the basics of the structure and look into something a little bit more intricate. And again, almost endless structural diversity is seen throughout nature. It's an enormously complex kind of foundation that we're building on. Okay, so there are basically 5 overarching themes in organic chemistry, and those 5 things are going to be highlighted as the main points in lectures 1 through 6. So basically, once we get through lectures 1 through 6, we hopefully will have laid the foundation that all of the other parts of the class can build upon. Okay, so those 5 themes are resonant. First one is resonance. So basically, what we've learned about resonance before is that these are different ways that a molecule can be connected only by changing the pattern of the bonding. We will see that by looking at resonance structures, we can understand reactive sites in a molecule. If you look at a molecule and look at its structure and consider any and all resonance structures, you will get a sense of where charge is located. Where is their positive charge? Where is their negative charge? Even if it's not a full charge, it could be a partial charge. And even that can serve as a guide to reveal reactive sites in a molecule. Second point is electronegativity. When I teach electronegativity in general chemistry, I say this is the single most important physical property concept that you can understand in chemistry. It impacts so many things. And here we go again. So electronegativity, we can look at polar bonds and polarity of a molecule, a molecular dipole, that are caused by electronegative atoms and see them as hot spots for where reactions occur. Okay. Usually the site of reactivity is determined by asymmetry in charge, and that's exactly what electronegative atoms cause. The third one is orbitals. Okay, simply being mindful of orbitals, where they are, what their shapes are, how big they are, or how dense they are, can help us understand, first of all, bonding. Okay, they can also help us determine molecular geometry, again, like using VSEPR theory, and that also can help us predict reactivity. Fourth, thermodynamics. So simple rules in thermodynamics will govern all processes in organic chemistry. So the idea that reactive species will react in order to form more stable products, or trying to reverse a reaction will require input in some energy. Trying to get a stable molecule to react will require a very highly reactive substance to kind of facilitate that. Those simple points are going to be highlighted a lot in this course. And fifth, trends. So in general chemistry, you probably learned a bit about trends such as atomic radius, or again, electronegativity, ionization energy, electron affinity. There are so many trends that we're going to see while studying this material. And if you can understand trends and kind of simplify things rather than having to memorize everything, look into the patterns, understand the patterns, that's going to simplify your life a lot, and that will be the secret to your success. In organic chemistry, you simply can't memorize everything. There's just too much material. So rather than trying to memorize everything, you look for patterns, you look for shortcuts. That's going to be a secret to your success. So as we go through these topics, I'm going to try to highlight these 5 things as they come up. Again, they will be recurring over and over and over. I'll do my best to highlight them. If you're taking notes, put a star by it. Anytime electronegativity comes up as a factor in something, or anytime orbitals come up, put a star by it and just note like, hey, look, we're talking about orbitals again here. That way, eventually everything will kind of fall into one of these 5 categories. So let's do a quick review. Now, this is strictly a review of atomic structure. This really should not be new to you. So first of all, an atom, okay, atomic structure, is a positively charged nucleus surrounded by a negatively charged cloud of electrons, okay? Remember that because of the size of electrons, how tiny they are, and how quickly they are moving near the speed of light, rather than thinking about electrons as moving around the nucleus in any kind of a defined path, we think of them as surrounding the nucleus in more of a cloud, a a defined cloud, but nevertheless a cloud, where anywhere within that region in space you can find an electron, right? So I have two new terms on the slide here that you probably aren't familiar with. The first one is electrophilic, okay? Something that is electrophilic, you can break down that word, is a lover of electrons, okay? Electrophilic. Something that is positively charged is electrophilic. That's the term we're going to use because it is attracted to negative charge. So the nucleus, we could say, is electrophilic. The electrons around the nucleus that are negatively charged, we would call them nucleophilic because they are lover of nuclei. They are attracted to positive charge. Okay? So keep those terms in mind because we're going to use them a lot in this class. Electrophilic is attracted to electrons. Nucleophilic is attracted to nuclei or simply positive charge. Okay, so electrons exist within these orbitals, which are discretely defined regions in space that correspond to a certain energy. Okay, so we have a couple orbitals drawn on the slide here. This is a 1s orbital here. It's a spherical orbital. That's the S. That's what the S means. The plot of electron density looks something like this, where at the nucleus we have highest electron density, and as we go out from the nucleus, the electron density decreases. And it's symmetrical on all sides because it's a perfectly spherical orbital. This is a 2s orbital. Again, since it's 2s, there are two layers to it. We have the 1s in the middle and the 2s on the outside. They are surrounded, or they are separated by a node. Remember that a node is a region in space where there is zero probability of finding an electron. Essentially, that is the region in space where the electron waves cancel each other out, right? Again, this plot looks something like this. We've got the 1s density towards the center. There's a node where there's no density, and then we have another wave of density for the 2s level. Right? We also have p orbitals. Remember that p orbitals are kind of barbell shaped instead of spherical shaped. So this picture here has the p in the x direction, p in the y direction, and p in the z direction. Remember, there are 3 p orbitals. That way we have 6 electrons in the p block, 2 electrons per orbital. And their density looks something like this, where we've got a node at the nucleus, which is noticeably different from the s orbital, which does not have a node at the nucleus. But the density in the p orbital lies farther away. The main most density in the p orbital lies towards a bit away from the nucleus, as opposed to the s orbital. Most of the density lies at the nucleus. All right? That should be pretty familiar to you. The arrangement of the electrons around the nucleus is also important. We've talked about the s block before, where atoms in the s block have valence electrons that are in an s orbital, and atoms in the p block have valence electrons that are in the p orbital. Now, here I took kind of a cross section of the periodic table that involves the atoms that are kind of relevant to organic chemistry. We're not going to deviate much from the second or third row, okay? We're not going to get into level 4, level 5. So at least looking at level 1 and level 2 here, we notice that we have 8 slots going from left to right. And again, going left to right, that tells us the number of valence electrons, right? So lithium would have 1 valence electrons in its level 2 shell. Beryllium would have 2 electrons in its level 2 shell. Carbon would have 4 valence electrons in its level 2 shell. And say for carbon, 2 of those electrons are in the s orbital, and 2 of those electrons are in p orbitals. For fluorine, we would have 7 electrons in the valence, with 2 of them being in the s and 5 of them being in the p, right? So we can count the electron configuration simply from the row of the periodic table and the column of the periodic table, and noting where the s block ends and the p block begins. Okay, so I'm using this term a lot, but valence electrons, remember, means the electrons in the outermost or the highest energy orbital. Okay, so carbon, again, would have 4 valence electrons. Hydrogen would have 1 because it's in column 1. Oxygen would have 6 because it's in column 6. Sulfur, right below oxygen, would also have 6, okay, because it's in the same column. Okay, and when we talk about reactivity, remember that it's the valence electrons that we're concerned with. Inner core electrons do not react. If they do react, it's in a very, very, very odd or specific set of circumstances. So it's going to be the valence electrons that are going to determine reactivity. So that's really all we have to look at. In all these cases, some of the electronic structure principles that we talked about in general chemistry also apply. Remember, the Pauli exclusion principle says that you can only have 2 electrons per orbital, and those 2 electrons always have to have opposite spins. Essentially, the Pauli exclusion principle says that no electron in an atom can have the same set of quantum numbers, meaning that you can't have 2 electrons in the same orbital and also have them with the same spin. They have to be in opposite spins. Okay, so for, say, neon, 2 of those electrons would be in the s block. Okay? 2 of them would be in the p block. 2 of them would, or in one of the p orbitals. 2 more would be in the other p orbital, and the last 2 would be in the third p orbital. That gives us 8 electrons distributed in 4 orbitals, 2 electrons per orbital, and those 2 electrons in each orbital will have opposite spins. Okay. Then Hund's rule says that electrons will singly populate degenerate orbitals before doubly populating them. So remember that the p orbitals, all 3 of the p orbitals that we showed here, where we had p in the x, p in the y, p in the z, those 3 are equal in energy. They are indistinguishable from one another other than the direction they happen to be pointing. So when we have degenerate orbitals like that, rather than populating them doubly, we populate them singly before pairing them up again. So carbon would have 2 in the 1s. That's 1, 2. Then 2 in the 2s. 1, 2. But then the last 2 electrons in the p block, we'd have 1 in the px, for example, and then 1 in the py, rather than putting them both into the px. That was Hund's rule. So if you're not familiar with the Pauli exclusion principle, Aufbau principle, Hund's rule, things like that, make sure you go back and review those. All right, kind of as a offshoot of the observation that a atom like neon is stable with 8 electrons, and beyond neon would be argon, also stable with 8 electrons. That is where we got something that we call the octet rule. So in 1915, a guy named G.N. Lewis, he was working at Berkeley at the time, was working on a theory called valence bond theory. And he was trying to basically explain how bonding works. He was using the observed periodicity and trends to connect that to bonding patterns and just develop a theory to try to understand what was going on. Why were we seeing these patterns, and why were these patterns, or how were they related to bonding? Okay. Now, the observation was that every 8 slots in the periodic table, basically, we encountered a very, very stable atom. And as we deviated from that 8th slot, the atoms got more reactive, and then they got less and less and less reactive as we went on. So because completely filled valence orbitals, again with 8 electrons, give rise to these very stable atoms, meaning atoms that don't react, the assumption here is that atoms will transfer or share valence electrons in such a way so as to achieve a fully filled valence shell for as many of the atoms as possible, right? That's the idea with either covalent bonding if we are sharing the electrons, or ionic bonding if we are transferring electrons, right? So if we look at sodium, whose electron configuration is 1s2, 2s2, 2p6, 3s1, and chlorine, whose electron configuration is 1s2, 2s2, 2p6, 3s2, 3p5, we see that chlorine is missing one electron from its valence shell. In the third level, it's got 7 electrons, 2 in the s and 5 in the p. So chlorine really wants one more electron in order to fill that third valence shell. If we compare that to sodium, it's only got 1 electron in its third level, but it does have a full second level, of course. So the idea that sodium will give up one of its electrons, its outermost electron from the 3s, and transfer it to chlorine means that sodium ion, Na+, will have a full second shell, and chloride ion, Cl-, will have a filled third shell. We have 2 ions that are very stable, and as a result of forming those ions, as a result of transferring that electron and giving us charge, those 2 particles will stick together as a Cl- Na+, and that is an ionic bond, okay? And that, the driving force, kind of the motivation of sodium and chloride to transfer that electron, is simply to achieve a full outer shell with 8 electrons. And for the elements that are concerned in this course in organic chemistry, a completely filled valence orbital will have 8 electrons. There are other atoms that can have more than 8 electrons in their valence shell. We call those hypervalent atoms, but for the purposes of this course, we're going to have 8 be the kind of ideal electron configuration. Okay, so I've alluded to this already. Ionic bonds involve actually transferring electrons from one atom to another to generate ions of opposite charges, which then kind of stick together like magnets, if you will, to form a compound. We just use sodium chloride as an example, but lithium fluoride is a similar example. Lithium has 1 electron, fluorine has 8 electrons. So by lithium giving up that electron to fluorine, we end up with a lithium plus ion, which is a helium configuration, and a fluoride minus ion that has a neon configuration. Those 2 ions will be attracted to one another, and they will make an ionic bond. Okay. I noticed that I'm using a notation here, this single-headed arrow, which is sometimes called a fish hook. I'm denoting the movement of this electron. This single electron from lithium is moving to fluorine. We're going to use this kind of arrow notation to denote movement of electrons. We're going to use that a lot in this class. So in this case, we're just talking about making an ion, but in other contexts, we're going to be talking about making covalent bonds or breaking covalent bonds or rearranging bonds, and we're going to use this kind of arrow notation in order to keep track of that. Okay, covalent bonds, on the other hand, instead of transferring electrons, covalent bonds would be where we are sharing electrons in such a way that both atoms that are sharing those electrons achieve a stable configuration, right? So if we look at hydrogen, here's hydrogen with 1 electron, hydrogen again with 1 electron. Rather than force one hydrogen to give up its electron and the other hydrogen to take the electron, we instead have them sharing those electrons. And in that sense, both hydrogens feel as if they have the 2 electrons. We don't have to steal 1 electron from the other in order to achieve that stable configuration. In this way, both atoms have that stable configuration, that helium configuration with 2 electrons in the 1s. Okay, so we can use this idea of pairing up electrons in orbitals to kind of guide us in determining how something is going to bond given some number of atoms that it has available to it, right? So let's look at nitrogen. For purposes here, let's imagine that the four edges of the atomic symbol here represent the four orbitals in the outer shell. So maybe one of these is the S, the other three are the P's, okay? Now, for nitrogen, it gets 5 valence electrons because it's in column 5, and those 5 valence electrons are sitting in 4 valence orbitals, okay? So let's fill those 5 valence electrons into those 4 valence orbitals using Hund's rule, in which we singly populate the orbitals before we doubly populate them. So we'll take the 5 valence electrons from nitrogen. We'll go 1, 2, 3, 4, 5. Okay? Now, that is the Lewis dot structure from nitrogen. We have 3 unpaired electrons and 1 set of paired electrons. So, in order to satisfy these 3 unpaired electrons, and in doing so, give nitrogen an octet, we need to bring in 3 electrons from some other source. So we could bring in a hydrogen with 1, say another hydrogen with 1, and another hydrogen with 1, and that gives us the Lewis structure for NH3, which is where we have 3 bonding pairs, 1, 2, 3, and we depict those as lines to indicate a covalent bond. And then we have a non-bonded pair, sometimes called a lone pair, that is simply sitting on nitrogen. So now this is just a theory of bonding. This was Lewis's approach to figure out how bonding was working. So good theory should be realistic and simple, okay? But really it should be as simple as possible. There is no truly complete theory of chemistry at this point, but we do have some very, very, very sophisticated theories that aren't particularly simple, but they do encompass as much as we can encompass within one theory. So again, we're going to start with simple theories, but as with any simple theory, we are going to get more difficult. And in order to encompass the more complicated structures, the more difficult kind of environments or variables, we have to make a more complicated theory in order to encompass that. So in regard to facts, okay, what a theory should do, it should help us predict facts. That's the big thing, okay? So if we can predict something, we have a power to understand something that's going to happen, or how something's going to happen, or how or why it's going to happen before it actually does. Even if something is not perfectly predictive, at least it could be suggestive of something, where it might say, okay, rather than predicting this one thing, it might suggest that 3 things might happen, or something, some combination of these 5 things might happen. It might give us a sense of where we're going. Below that, though, a theory that does something below suggestion is not particularly useful, like explaining something. That's called postdiction, when a theory explains something, but it can't predict something. It's only good for knowing something after the fact, which, what's the point, right? And then finally, classification and remembering. That might be something that a theory can do, but it's not what makes a good theory. The example that I like to use is Roygbiv, right? ROYGBIV. That is a way for us to remember the order of wavelengths in visible light: red, orange, yellow, green, indigo, violet. But that's not a theory. It doesn't help us predict anything. It doesn't help us predict what might come before red or what might come after violet, okay? It only helps us remember something, and maybe it can help us classify something. So keep this in mind as we go, because we're going to be using a lot of different theories. we're going to be developing theories and expanding upon simpler theories. Okay? This theory is a simple theory of bonding where we simply pair up valence electrons in order to have 8 electrons in as many atoms as possible. These structures, like I mentioned, are Lewis structures. So we are basically taking an atom with its valence electrons and arranging those valence electrons with other atoms so that as many atoms as possible can have a full valence shell. So the way we're generally going to do this is we're going to count the valence electrons in each atom. We're going to arrange the atoms in such a way that all atoms achieve an octet. 2 dots make a bond, so 2 electrons make a bond, and we represent that as a line. And this is, strictly speaking, this is convention. This is a way for us to represent or communicate what a chemical structure looks like. This is not a perfect picture of what a molecule looks like. Methane does not look like this, okay? Ethane does not look like this. The structures in reality are significantly more complicated. There's much more to it than this, but this gets at the heart of it. This is a simple way to explain what we observe, okay? That we observe that carbon is bonded to 4 hydrogens, that those 4 bonds are equal, that kind of thing, okay? But it, in a lot of ways, it also hides our ignorance about what we don't fully understand, okay? And we'll get into that more, but just keep that in the back of your mind, okay? This is not a perfect picture. It might look nice, but it does hide a lot of our ignorance. If you follow this pattern that we've been using, you will notice bonding trends, okay? We already looked at nitrogen, where we had nitrogen had 3 bonds with a lone pair, and we figured out that in order, starting with 5 electrons that nitrogen does, we needed 3 bonds to give it 8 electrons. If we go back and we say carbon's got 4 electrons, it's going to need 4 bonds to get those remaining 4 electrons. Oxygen with 6 electrons is going to need 2 bonds in order to achieve that 8. Chlorine with 7 electrons is going to need 1 bond to make 8. And hydrogen with 1 electron is going to need 1 electron to make 2. Remember that only hydrogen has that only 1 s orbital, so it only needs 1 electron to make that bond. So if you look at this pattern, this trend, bonds versus lone pairs, bonds for carbon 4, bonds for nitrogen 3, bonds for oxygen 2, bonds for hydrogen and the halogens like chlorine 1, okay? Lone pairs 0, 1, 2. Hydrogen has 0 because it can only have 2 electrons total, but halogen would then have 3, right? So we've got a trend here, okay? We've got a trend 4, 3, 2, 1 and 0, 1, 2, 3. And specifically, if we take 8 minus the number of bonds that we make, so 8 minus 4 for carbon, 8 minus 3 for nitrogen, 8 minus 2 for oxygen, we end up with the number of valence electrons, right? So fluorine, 8 minus 1 bond, has 7 valence electrons, or column 7, column 6, column 5, column 4, okay? So basically, the number of electrons that each atom needs in order to achieve an octet will be the number of bonds that it makes, okay? And the number of lone pairs is the number of remaining or non-bonded electrons divided by 2. So if we have 6 valence electrons remaining, after using 2 for a bond, we'll have 3 lone pairs. Electronegativity is another term that I want to review here. Make sure everybody's on the same page because it is indeed a very important topic. Remember, electronegativity is basically the tendency of an atom to draw electrons toward itself. This is simply a property of atoms. Some atoms tend to pull electrons toward themselves more than others do, okay? It's basically a function of the number of protons in the nucleus and the number of electrons and the valence electrons and the distance of those valence electrons from the nucleus. We've got more protons in the nucleus for larger atoms, so that's going to mean more pull. That's generally going to mean more electronegativity. So that's why as we go across the periodic table, we get more protons, and so we're going to have more pull. So electronegativity is going to increase from left to right. But as we get more electrons, and you get those electrons farther away from the nucleus, you're going to get less attraction, less pull from the nucleus. So that's why as we go down, these electrons that are way out far away in the fifth and sixth and seventh shell are not going to be as attracted to the nucleus, so they're not going to get pulled as tightly towards the nucleus. So there's kind of a counterbalance there. And so it figures that there's going to be, if there's a balance, there's going to be some place where this property is maximized. And it turns out that that place is fluorine. Fluorine gives us the optimal combination of positive charge in the nucleus and electrons that are close enough to that charge to actually feel it without having too many other electrons getting in the way. So this table here has a number on it for each atom. And that number is, it's part of what's called the the Pauling scale. Another scale you might ever see is the Mulligan scale. But generally speaking, the Pauling scale is the most popular scale. It simply goes from 1 to 4 in ranking how electronegative an atom is. Now, the difference in electronegativity, the differential between two atoms that are bonded to each other, will generate a dipole because one atom is pulling harder on the electrons in the bond than the other atom is. Take, for example, carbon and chlorine. So carbon's electronegativity on the Pauling scale is 2.5. Chlorine's electronegativity on the Pauling scale is 3. So there's a significant difference between carbon and chlorine, meaning chlorine's going to pull harder than carbon. So there's going to be a partial negative charge on chlorine. There's going to be more electron density over by the chlorine and less electron density over by the carbon. So we say this is delta negative and this is delta positive, okay? And we can represent that differential with this dipole symbol. It's an arrow that says the direction that the electrons are being pulled from the carbon to the chlorine. And then at the tail of the arrow, we put a plus sign to indicate that the positive end is carbon. You can look at, this is called an electron potential map that just shows the electron density as a surface of this molecule. And you can see that definitely there's lots of electron density over by the chlorine, less by the carbon and the bottom end of this molecule. You can combine these dipoles to make what are called molecular dipoles. So here's ammonia. Ammonia has 3 bond dipoles, hydrogen to nitrogen, where hydrogen is the positive end, nitrogen is the negative end. Again, if we go back and we look at our table, we've got hydrogen at 2.1 and nitrogen at 3. So that's, again, fairly large, 0.9 difference in electronegativity. So those are going to be fairly large dipoles. Notice that along the bottom of this molecule is all the positive charge, and towards the nitrogen and the lone pair is all the negative charge. So that net effect is to have the positive end at the bottom and the negative end at the top, and that is what we see with this electron potential map here. That is called a molecular dipole. A molecular dipole or dipole moment is basically the spatial or directional sum of the individual bond dipoles. So when the molecular dipole is non-zero, when there is a net differential in charge from one end of the molecule to the other, we say that the molecule is polar. That's how ammonia works. That's also how water works. Again, we've got hydrogen and oxygen. If we go back to our Pauling scale, hydrogen is 2.1, oxygen is even 3.5, even a larger 1.4 differential in Pauling scale. So it's going to be a very large dipole. But the hydrogens are on the bottom part of the molecule, and the oxygen with its lone pairs are on the top of the molecule. So we have directionality. We've got a negative end on one end and a positive end on the other, and that gives us a dipole. This dipole symbol is mu, the Greek letter mu, and this can be quantified. Ammonia is 1.47 dBi, that's the unit dBi, and water is 1.85. So because this is a larger dipole for hydrogen to oxygen, the molecular dipole is going to be larger for water. Now, sometimes you can have bond dipoles that oppose each other. So here's carbon dioxide, and we've got, again, two dipoles, carbon to oxygen. We can check our numbers. Carbon is 2.5, oxygen is 3.5. So that's significantly different. And we have the positive end on carbon in both cases and the negative end on oxygen in both cases. But if we look at that structure for carbon dioxide, we actually don't have a dipole. We don't have two poles. This molecule has only a negative end and another negative end. There's no positive end to this molecule. In fact, these dipoles directly oppose each other in direction and strength. And that essentially causes them to cancel each other out. The same thing is true for something like tetrachloromethane here, where we have carbon with 4 chlorines all pulling in different directions. Now, all these dipoles are equal, and as you can see, the net effect is that there is no negative end or positive end. Okay? The electron density is basically spread out equally around this tetrahedron. So in those cases where you have equal dipoles that are all opposing each other, you end up with a non-polar molecule. So a polar molecule has that differential in charge. A non-polar molecule has no differential. And this really affects how a molecule behaves. So again, understanding electronegativity can help us understand dipoles. That can help us understand, in conjunction with molecular shape and VSEPR theory, that can help us understand how a molecule is going to behave, say, with other molecules. Maybe a molecule is going to be attracted to the positive end of water, or the negative end of water, or the negative end of ammonia, or the positive end of ammonia. Okay. What we're building here is a way to predict the properties and therefore behavior of a molecule. Okay. We can have nonpolar, where electrons are shared equally. We can have polar, where electrons are shared unequally. And eventually, if the inequality in this bond is great enough, eventually the electrons will be completely transferred. Okay, so this is a continuum. Now, let me point something out. For hydrogen and carbon, the difference is only 0.4. And it turns out that for a differential of 0.4 or less, the dipole is not noticeable. There are techniques that you can use, very sensitive measurements, where we can see the dipole, but generally speaking, anything less than a 0.4 difference in the Pauling scale between two atoms, we're going to consider it nonpolar. So carbon to hydrogen, we're going to call nonpolar because it's 0.4 or less. On the other hand, anything greater than 1.8 is so large that the bond actually breaks. It actually stops being a covalent bond, and the electrons become transferred to become an ionic bond. So something like sodium, 0.9, and chlorine is 3. That's a differential of 2.1. So that's greater than 1.8. And so that will cause the bond to snap. Basically, that's what we're showing here. The bond becomes so great that eventually it snaps, and both the electrons end up on chlorine instead of them being shared. So keep that in mind. Nonpolar is 0.4 or less. Polar is going to be 0.5 to 1.8 in differential, and ionic is going to be about 1.8 or greater. Okay, one more aspect to a Lewis structure is something called formal charge. And this is another extremely important thing. I feel like I've been saying that over and over and over, that all these things are extremely important. But that's true. All of these things are important. That's why we cover this in lecture 1, is so that we can build upon this as we go. So what is a formal charge? A formal charge is simply a method of bookkeeping for electrons, all right, where we can keep track of which atoms are electron rich, meaning again, they're nucleophilic if they're electron rich, and which atoms are electron poor or electrophilic in a molecule. This basically serves as a guide, again, to help us predict reactivity. And the formula for formal charge is the group number, so the number of valence electrons that the atom comes with, minus the number of bonds, minus the number of lone electrons. I'm going to highlight how this works using ammonia and ammonium as sample molecules. So let's draw ammonia. We've done that before. Ammonia is NH3. So we start with the N. And remember, we went 1, 2, 3, 4, 5 for that. And then we added a 1 electron from hydrogen, another electron from hydrogen, and a third electron from hydrogen. And in doing so, you see that hydrogen ends up with 2 electrons each, and ammonia nitrogen, ends up with 8 electrons. So let's go through and calculate formal charge. Remember, formal charge is going to be group number, or number of valence electrons, minus the number of bonds, minus the number of lone electrons. Okay? So nitrogen is group number 5. We'll say nitrogen is group number 5. We're going to subtract off 3 bonds, the bonds to hydrogen, and then we're going to subtract off 2 lone electrons. So nitrogen's formal charge is 0. Okay? No formal charge. It's effectively neutral. Okay? We can do the same for hydrogen. Hydrogen is group number 1. Subtract off 1 bond. Subtract off no lone electrons. Hydrogen's formal charge in ammonia is 0. Okay? That's basically a good thing. That means that this molecule is fairly stable. Now, instead of using ammonia, let's use NH4 plus ammonium. Draw it down here. So this looks like this. It's NH4 and I said it's NH4 plus. I'm going to write the plus charge out of the way for now because I want to assign it to an atom, but I don't want to give away what it is yet. So let's go through and calculate the formal charge now for all of these atoms. Okay? Let's start with hydrogen because you're probably noticing that for hydrogen, it's the same, right? In all of these hydrogens, we have 1 valence electron, it's from group 1, and all of these hydrogens have 1 bond. So for hydrogen, and also 0 lone electrons, which means that the formal charge for hydrogen again is 0. So where is this formal charge coming from? This charge that I'm telling you is there. Well, it's on nitrogen. If you figure out nitrogen has 5 valence electrons minus 4 bonds minus 0 lone electrons, you see that now nitrogen has a formal charge of 1. This positive charge on nitrogen, this formal charge in ammonium is actually on nitrogen. It belongs to nitrogen. And if we compare ammonia to nitrogen, you'll notice that whereas nitrogen in ammonia was sharing the 3 bonds, but had an entire lone pair to itself, that lone pair is gone in ammonium and is instead being shared with an additional hydrogen. So instead of having 2 electrons to itself, it's now sharing 2 electrons. And that difference, the difference between sharing 2 and hogging 2 all to itself, causes it to effectively have 1 less electron all to itself. And so even though in both cases, nitrogen's got 8 electrons, it's got 8 in ammonia, 3 in 3 bonds, so 6 electrons from the bond and the lone pair, and 8 in ammonium from 4 bonds with 2 electrons each. Both cases have 8 electrons around nitrogen. It's the arrangement of those electrons that's different. And that is where formal charge comes from. So let's go back to our slides and let's look at another example where we can calculate formal charge. So again, we've got formal charge is the group number or the number of valence electrons minus the number of bonds minus the number of lone electrons. And let's do hydrogen first. So hydrogen, 1 bond or 1 valence electron minus 1 bond minus no lone electrons means 0. Same thing for the other hydrogen, 1 group 1 minus 1 bond. The third hydrogen, group 1 minus 1 bond. We can look at carbon. Carbon is group 4. Subtract off 4 bonds and subtract off no lone electrons. It's going to be 0. The other carbon is the same. It's also got 4 bonds. Now, the arrangement of the bonds is different. Instead of being 4 single bonds, it's 1 single bond and 1 triple bond, but it's still 4 bonds and no lone pairs. And so we end up with a formal charge of 0. And then nitrogen, like we did before, group 5 minus 3 bonds in the triple bond minus 2 lone electrons makes formal charge of 0. So in this molecule called acetonitrile, all the formal charges are 0, meaning that this is a fairly stable molecule. This is a good arrangement of these electrons. The arrangement of these electrons is as ideal as we can get. Now, if you make a table like your book did for you, where you have different bonding arrangements for these different atoms, you will see a trend, okay? That carbon with 3 bonds has a positive charge. 3 bonds and no lone electrons gives carbon a positive charge. 4 bonds will be neutral, and 3 bonds with a lone pair will make it negative. And if you go through and calculate the formal charge yourself, you'll understand why this is negative and why this is positive. Nitrogen, 4 bonds like we calculated is a positive charge. 3 bonds with a lone pair is neutral. 2 bonds with 2 lone pairs is negative. Notice that every time we turn a bond into a lone pair, we go down in charge from 0 to -1. Here, from 0 to -1. Okay. Turn a bond into a lone pair, goes from +1 to 0. Okay. Oxygen with 3 bonds and 1 lone pair actually has a positive charge. Again, calculate that. You'll find that it's positive. If you turn a bond into a lone pair, we go from +1 to 0. If we turn another bond into a lone pair, we go from 0 to -1. Okay. You can follow the pattern. I would advise you to go through these bonding arrangements and calculate the formal charge for yourself. Figure out, prove to yourself that the positive charges are there, or the neutral charges are there, or the negative charges are there. Now, generally speaking, formal charges of +2 or -2 or greater are basically forbidden in organic chemistry with covalent compounds. We really don't deal with charges more than +1 or -1. So if you ever see a structure with a +2 or a -2, um, either the structure is wrong. If you say maybe you drew it and that's a way you're going to check, it's a probably incorrect structure. Or if it is +2 and it's actually correct, it's a very, very unhappy or very reactive or unstable molecule that might not even really exist in reality. Okay, so pay attention to those trends. I would recommend memorizing this table as quickly as you can. Even if it's not memorizing it, eventually you'll do it so much that it'll become second nature in calculating these things. But just be aware of what these bonding patterns look like, and you'll be in good shape. One last thing I'd like to cover is that notation that I mentioned in one of the first slides, where I was showing you these molecules that had these carbon scaffolds that were drawn as lines and angles. This is a type of notation called line angle formula. What this is a quick and geometrically correct way to represent these organic compounds. It's going to simplify your life a whole lot and make you very, very, very fast at drawing these molecules. So here's the principle. What we have here are two of the same molecules, one being drawn as a proper Lewis structure, a molecular formula, and the other one is the same molecule, but represented in line angle formula. So what we're going to do is we're going to represent bonds as lines. That doesn't change, right? We're using bonds as lines here, bonds as lines here. So we've got a single bond, a double bond, single bond, double bond. Same thing here, single bond, double bond, single bond, double bond. But carbons are implicit at the vertices. So we actually don't really draw any of these carbons. But we know that at the vertex of these lines, there is a carbon. So there's a carbon there, carbon there, carbon there, carbon there, carbon there, carbon there. Okay. At the ends and angles of these lines are a carbon. Okay. Charges are always drawn when they're present. So if you go through and calculate formal charge for all of these atoms, you will find that in fact there is no formal charge in any of these atoms, which is why there are no charges drawn here. Also notice that the hydrogens are implicit when bound to carbon. All carbons are assumed to have enough hydrogens to fill all the valence, right? So this hydrogen, or this hydrogen, or this hydrogen, or this hydrogen, any of the hydrogens that are bound to carbon are just left off the structure. We don't even bother drawing them. We do draw hydrogens that are attached to other atoms. So a hydrogen on an oxygen, we do draw that in. Okay. So when you're reading a line angle formula, like I say, all carbons are assumed to have enough hydrogens to fill the valence. What do I mean by that? Well, this carbon here, for example, has 3 bonds drawn to it. We've got the single bond drawn to the left, the double bond drawn to the right. That's 3 bonds drawn. And this carbon does not have any charge on it, which means that there must be one more bond. Remember that a neutral carbon, a carbon with no charges, has 4 bonds. So where is the 4th bond? It must be to hydrogen. There must be a hydrogen there. Same thing here. Also 3 bonds drawn, 1 and then 2 in the double bond, and there's no charge on this, so there must be a 4th bond somewhere. That's the hydrogen. What this effectively does is it highlights the most important aspects of a molecule structure. We see where are the single bonds, where are the double bonds, Where are the important atoms? Now, this is not to say that carbons aren't important, but they are a nitrogen is going to be much more important to the reactivity of this molecule than a hydrogen is going to be, for example, or a double bonded oxygen or an OH. These, what you're seeing here, the double bonds, the nitrogen, the double bond to O, the OH, those are the important aspects of this structure. Now, this is the de facto standard for drawing molecules. Most organic chemists would never draw this molecule in this explicit format with every single atom written in. They would almost 100% of the time draw it using line angle formula. I will do it that way. I will use line angle formula pretty much exclusively. Any other students that have taken organic chemistry before will draw molecules this way. Any other professors that you'll run into on your campus would draw molecules this way, as long as they're relatively familiar with organic chemistry. This is how it's drawn. So please practice reading structures this way and practice writing structures this way. Going back again to our picture from before, practice reading these things. Go through and figure out how many carbons are in the molecule or how many hydrogens are on each carbon. Maybe you want to practice converting a a line angle structure into an explicit structure. Try drawing cocaine in an explicit structure, or try drawing testosterone in an explicit structure. Okay? Just get practice reading and writing these things. Notice, however, there are some things that are interesting here. Notice that testosterone in this structure has some hydrogens drawn in. That's a hydrogen that's on a carbon. That's a hydrogen on a carbon. That's a hydrogen on a carbon. Same thing here in morphine. There's a hydrogen drawn that's attached to a carbon. You can sometimes, for important reasons, draw in these hydrogens, okay? This hydrogen is drawn there to show that it is a wedged hydrogen. These guys are drawn in to show that they are a dashed hydrogen. There is a reason to draw that hydrogen. So it's not necessarily wrong to include a hydrogen or even to draw a carbon sometimes. It's just that the only really reason to do that is if it matters, if there's some logic behind it. Otherwise, they're just drawn as lines or angles if they're carbons, or ignored entirely if they're hydrogens. This is another one of my favorite molecules. This is strychnine. It's a pretty cool strychnine. It's a poison. It's a pretty cool structure if you look at it. Almost every atom in this structure is in a ring. We've got a 6-membered ring here out of carbons. We've got a 5-membered ring here where one of them is a nitrogen. Here's another 6-membered ring. This is a 7-membered ring. I believe this is an 8-membered ring. 1, 2, 3, 4, 5, 6, 7, 8. 8 or 9 members in this ring. Almost everything's in a ring except for this double bonded O and the hydrogens that obviously can't be in a ring because they can only make one bond. Again, notice the geometry. These wedges and dashes specify the geometry, and we'll get more into that later. But the point of drawing this hydrogen here is to show that it's going down into the board, kind of behind the screen. And this hydrogen here is kind of a wedge that's coming up into the screen. If those weren't there, or if they were just drawn as lines instead of dashes or wedges, we wouldn't know what direction they're going. And it turns out that that's very important to the structure of strychnine. And so that's why they're drawn in there. Okay, I have some practice here. I'm going to leave this on the screen. You can pause it while you work on this. But try to convert the condensed structural formula into line angle formula. Go ahead and practice this now. Go ahead and pause the video and draw those out. And tomorrow in class, we will go over those answers. You can compare your answers to mine, and I'll also post those up to Canvas so you can have them at a later date. For now, I want you to start memorize something that are memorizing something that are called functional groups. I have the slide that summarizes what are called functional groups. These are groupings of atoms that have some chemical function. They are reactive. So each of these has a class. So an alkane, an alkene, an alkyne, borane, a carbonyl, a carboxylic acid, an ester, an amide. Here is the explicit formula for an alkane. There is an abbreviated formula where the explicit formula is kind of condensed. And this source that I got this from calls this a stick, but the stick formula, as you can see, is a line angle representation of the explicit formula. Some things to note here: an R group simply is a carbon group of some kind, meaning it's just another carbon. We're not specifying what it needs to be. Other things: an X is an alkyl halide. So an X can be fluorine, chlorine, bromine, or iodine. An M is a metal. And I think that's all. So here we have an X, that's going to be a halogen. An R group would be just a carbon. So memorize these kind of arrangements. An alkane is all singles. An alkene is a double bond. An alkyne is a triple bond. A cyclopropane is a three-membered ring, 3 carbons in a ring. An alkyl halide is a carbon, an R group, some kind of carbon with an X on it, so X being a halogen. An alcohol is a carbon group with an OH, right? So try to memorize those. You might want to make flashcards for those. If you have any questions, you can ask me at any time. You can also look them up in the book. Your book is basically divided into chapters where each chapter focuses on a type of functional group. That is all for lecture 1. The Stromanus book that corresponds to the material from this lecture is chapter 1. We will go over chapter 1 in Stromanus, and that will be part of your workshop in class tomorrow.